So actually the way it will appear is it will be like as if you're sampling this waveform. It'll kind of appear as if you're sampling this frequency response that you have done. If you make a periodic signal, it is something like sampling this particular frequency response.
Okay, thank you.
Yeah.
Yeah, please continue, Srini.
Yeah, so typically when you're looking at a frequency response of a system, so why is the frequency response of a system very important? Because you want to know what. So suppose so what we studied so far is a signal can be broken down into its component sine waves. Therefore, if I know how a system responds to various sine waves, then I'll be done. Then I kind of know how the system is going to behave. Yeah. So what does a Fourier transform of a so what does the transfer function essentially give you? It gives you the Fourier transform of the impulse response. Yeah. Why is this very important? Because the impulse response contains all possible frequencies. The impulse, the impulse response is the response to of the system to an impulse. Now, impulse has all frequencies. Yeah? Impulse is a summation. So if I look at the frequency response of an impulse, it's a flat frequency response. Yeah, therefore it has all frequencies with the same amplitude. Yeah, therefore if I know how a system responds to an impulse, I know how it's going to respond to every possible frequency. Yeah, so it becomes very important for you to study the frequency response of the impulse, the frequency response of the impulse response. Yeah, you want to see the Fourier transform of the impulse response. Yeah, so that kind of becomes extremely important. So how do you interpret this graph? Yeah, suppose I give you this. So this Bode plot is nothing but the frequency response. It's a frequency response that's normally plotted on a logarithmic scale. Yeah, that's just a Bode plot. So Bode plot is nothing but just the frequency response. So how do you interpret this particular thing that we see here? So suppose I have a system that has this as a frequency response. What it means is that if I look at a certain frequency, suppose I look at 0.1 hertz and I see what happens at 0.1 hertz. So I have two values here for 0.1 hertz. Yeah, I have the magnitude, which is given in the red plot here, and I have the phase delay, which is given in the blue plot here. Yeah. So I need to see. Suppose I see where the magnitude is. So you have it as something like around minus 14 decibels. Yeah, which would mean that you would have an attenuation of minus 14 decibels. Yeah, that is, if I give a signal which has 0 decibels, the output would be minus 14 decibels. Therefore, it would be attenuated by minus 14 decibels. Your signal would be so it will kind of be the log inverse of it will be like so if I look at minus 14, it is like the log inverse of minus 14 would be like the gain of this. Yeah, so you would have you have an attenuation of minus 14 decibels for a signal whose input is 0.1 hertz. Yeah, which means the signal magnitude is going to reduce by that much. And the second important thing is you have this phase that you see here, which means that you have a phase delay of 30 hertz, which means that your output signal will deviate from the input signal by an amount of 30 degrees. Yeah, that means your signal would be delayed at the output by an amount of 30 degrees, which it kind of defines with how much delay will that signal appear at the output. Yeah, so you have a signal that's going to be attenuated by minus 14 decibels, and you would have a signal that's going to have a delay of minus 30 decibels, minus 30 degrees. Now, what you would want is, ideally, you would want this. So as the phase delay becomes higher, yeah, you would want the corresponding signal to be attenuated very strongly. Because if a signal with a high phase delay starts appearing at the output, yeah, then that means that, so now let's see what happens. So if you see the combination of this thing at the lower frequencies, yeah, if I look at say 0.001 hertz, if I look at this extremely low frequency, you have hardly any attenuation. Yeah, so it's like 1 dB attenuation or something of that sort. So it's very little attenuation. You will practically be hearing the same signal back. Yeah, at this point, what happens is that your phase is not shifted by much. It's hardly shifted by 3 or 4 degrees, which means that your output would come at exactly the same time. There's no delay between the input and the output. For the lower frequency signal, that means for the signal that has, say, a more heavy bass kind of a sound, your output is going to appear at the same time. Yeah. But as your frequency increases, slightly higher pitch signals are going to be attenuated more, but they're going to appear later in your output. Yeah. Now, what happens in an impulse? All frequencies have zero phase. Yeah. Therefore, they appear at the same time at the output. But once your impulse passes through this system, it is going to bring about greater delays in some of the higher frequency components. So as your frequency increases, your phase kind of delay increases. Therefore, your higher frequency components are going to appear later in your output, which means your input was an impulse, which was like a clap. Yeah. At the output, because of these phase delays, this clap is going to get smeared a little bit. Yeah, your clap is going to be heard for a slightly longer time. Yeah, you will kind of see this clap being spread across in time. Yeah, so that's what happens. So the difference that you can see is probably if you hear a mridangam. Yeah, a mridangam has a very sharp sound. Yeah, it kind of disappears very fast in time. Whereas a pakavaj is going to last much longer in time. Yeah, so if you have a filter of this kind that is shown here, this is a low pass filter. This is a transfer function of a low pass filter. Suppose I have a system with this kind of a transfer function. If you give an input as a mridangam to that particular system, your output will now appear like that of a pakavaj. Yeah, which is going to be a sound that's that's more delayed, that's more resonant, and it occurs for a longer period of time. Yeah, so it kind of smears your signal a bit. Yeah, so I hope that concept is kind of clear. Yeah, so your whole system, your speakers, your signal processors, all of them are essentially systems in the middle. So they are going to appear as transfer functions. Yeah, so you need to adjust the transfer functions of these devices in the middle so that your output response is as you want. Yeah, typically you would want the output to be to reproduce what is there on the input side. So suppose I play the violin onto a mic, I would expect that the speaker should reproduce what I'm playing. If I suddenly hear that the speaker is producing sound with varying delays and it doesn't sound like my violin, then I'll be very disturbed about it, right? So so you would want that in the range of frequencies that the input is, the speaker or the whole system response should probably amplify signals in the way we want, but they should not bring in unneeded phase delays. They should not change the nature of the signal at the output. Yeah, so if for your signal to be reproduced faithfully at the output, you would want your frequency response to be flat in the operating range. Yeah, so so let's see. So for that, we try designing various kind of filters. Yeah, and we'll see what they are. So typically, we can look at three particular types of filters: say low pass filters, band pass filters, and high pass filters. So low pass filters are those filters that pass the low frequencies. Yeah, they are filters that allow frequencies closer to your base frequencies to pass, but they will attenuate the higher frequencies. Yeah. So typically, low pass filter is like the filter that we just saw there. It will it'll kind of convert a mridangam to a pakavaj. It will kind of smear your signal a little bit. Band pass filters are used when we want to pass only a certain band of signals, and high pass filters are used when you want to pass higher frequency signals and kind of not look at the lower ones. So typically, when you want to amplify very sharp sounds, yeah, you would typically be using high pass filters. Yeah, and you look at the frequency response of low pass filters. So you see here, there's a whole pass band. So typically the setup. So what you would want is, you see that there are two things that I would want you to observe here. First is that there is this whole band of frequencies where your amplitude is 0 dB. Yeah, which means that your signal amplitude does not change. Yeah, this is a flat. This kind of gives you the amplification that you initially have. So the input and the output would have nearly the same loudness. Yeah, for an amplifier, you would typically want this graph to go slightly higher. Yeah, and but the important thing is this part of the frequency response is flat, which means the amplitude magnification for frequencies in this range is going to be approximately the same. Yeah, therefore, from a pure amplitude point of view, when you're operating in this range, your from an amplitude point of view, your reproduction would be faithful. And similarly, if you look at the phase part, the phase part is initially flat, but even before your magnitude begins to fall off, your phase begins to fall off. Which means that if you look at this particular band of your frequency response, although, so I just probably capture this whole thing off. So if you look at this particular band, your amplitude response is nearly flat, which means that the magnification that different frequencies have is not very different, but your phase delays begin to change. So higher frequency signals in this range have greater phase delays, and the lower frequency signals have lesser phase delays, which means that your signal will start getting spread in time. Although there would be no distortion so far as the magnification is concerned, you will begin to have distortion so far as your phase is concerned. You will start having the signal the signal will begin to spread out in time. If I'm playing something on the violin, you will suddenly see you'll see that the sound is kind of getting smeared, right? It's kind of spread slightly out in time. So if I'm trying to play the violin very fast, you will start seeing the corresponding. So when suppose my speaker is tuned in this particular region, you will see that the frequency amplitudes are all right. But if I'm trying to play very fast, before my re ends, when my G starts, the speaker is still giving the sound of the re. Therefore you will have the re and G kind of merging into each other, and you will have slight distortion of sound that will take place. So that's what would happen in this region. So typically you would want your system. You would want to tune all the parameters of the system so that you operate in this region. Therefore, you want to tune your filter parameters in such a way that for the frequency band in which you're operating, both your frequency and both your magnitude and phase responses are nearly flat. So the next kind of filter that you have is a band pass filter. So here you're just trying to allow a certain frequency band, and you're trying to push out every other frequency band. So you see here you have this pass band that's flat, but again here your phase keeps varying. You want to operate at a region wherein your phase distortion is as close to 0 as possible. So here you're allowing a certain frequency band in the middle. You're clipping off everything that has a lower which has a lower frequency than a given frequency, and you're kind of clipping off everything that has a higher frequency than a given frequency, and just looking at all the frequencies that are there in the middle. This is a band pass filter. And lastly, you have a high pass filter. So this is not a band pass filter. This is a high pass filter. So lastly, you have a high pass filter. So what happens in a high pass filter is that high frequencies are passed and the low frequencies are typically thrown out. So what happens in a high pass filter is that so why do you design low pass filters? You design low pass filters in order to filter out noise. So typically noise would occur as high frequency components. You would have in this flickers and all these kind of things that happens, the noise that the mic picks up, the noise that other system parameters, you have this just something that happens because of transistors inside. So all of them are small signals that get added on to your original signal, and those signals essentially reflect as high frequency components. It's the high frequency components of those signals that produce a kind of noisy effect. So in order to filter them out, you would need to use low pass filters, because they attenuate the high frequency components of the signal. Band pass filters are when you're trying to look at particular frequencies in particular. High pass, why would you need high pass things? Wherein you're trying to recognize sudden changes of sound. So suppose you want something to, suppose you have a low pass filter, as I told you, it will start distorting a clap. Now, suppose you have these very sharp claps and you want to produce them as it is, you will need a high pass filter for that. You will need to take out the high frequency components and want to make them behavable. So what happens in a high pass filter is you have zero phase distortion only for high frequencies. Right? For high frequencies, you have zero phase distortion. For the low frequencies, you have attenuation as well as you also have phase distortion that takes place. For the high frequencies, you do not have phase distortion. Your phase is nearly zero. That means your input and output would occur at approximately the same time. You do not have the signal shifting in time. Yeah, that's what a high pass filter would do. Yeah. So the next is these filters are implemented using so what do you do when you want to implement this on a computer or a DSP or something of that sort? You would want to implement them using equations, right? You'll be writing equations to implement them. So now there are two kinds of implementations that you can have. You can have an IIR implementation or you can have an FIR implementation. So what is an IIR filter? IIR filter just means a filter whose transfer function, yeah, suppose you apply an impulse to an IIR filter, the time response theoretically goes on till infinity. Yeah, suppose I apply an impulse. So for example, if I look at the system here, so you have y of n is equal to 0.1 y of n minus 1 plus u of n, right? Now u of 0 and y of minus 1 are both 0, right? So if I apply u of 0 as 1, so at the first time instant, y of n would just be 0.1 into 0 plus 1. Yeah, so y of 1 would be 1. So now after that, your u of n goes to 0. So then you will just have 0.1 y of n minus 1. So from 1, you will go to 0.1, to that you'll go to 0.01, to that you'll go to 0.001. You will keep reducing, your signal strength will keep reducing with time, but it will never go to 0. Yeah, so your impulse response technically goes on for infinite time. It's a different thing that ultimately your physical systems are made by yeah, they behave like band pass filters. You give them very, very low frequency, they simply will not respond. Yeah, they'll respond around their resonant frequency. So typically very low signals would not, your physical systems would not respond to them and you would not hear them at the output anyway. Yeah, but technically inside the processor, your signal kind of goes on forever. Yeah, your signal never completely dies down. That's an infinite impulse response. It just means that your impulse response lasts for infinite time. It never really dies down. Yeah, what characterizes them? There is some amount of feedback that is needed for an infinite impulse response. That is, the output at time instant n depends upon the output at time instant n minus 1. Yeah, it depends upon the output at time instant n minus 1. Yeah, and so your output depends upon past output. So whenever you have that particular characteristic, you would have an infinite impulse response filter. Yeah, and a finite impulse response filter is nothing but a filter wherein the response occurs only for a finite amount of time. Yeah, and after that the output is just going to be 0. So typically here your your output is just going to be a combination of it's going to be a linear combination of inputs at various points. You have no the expression for the output does not have any term that includes the past outputs. Yeah, it has only past and current inputs. So the moment your input goes to 0, eventually your output has to go to 0. Yeah, because there is no memory involved. Yeah, so there's no memory at the output involved. There's no feedback involved. Yeah, so that's what an FIR filter is. So typically, what you would want is so filter design is always done in the IIR sense. Yeah, suppose I want to so if you see the steps of filter design, normally even if I have so a lot of these signals are implemented on DSP. Yeah, a lot of the signal processing happens on DSP process or DSP boards. However, initially your signal is always heard. Your signal, what we speak here, is always analog. Yeah, it's a continuous time signal. Yeah, your signal is not discretized when you're speaking. Now, what happens is you sample the signal. That is, you listen to the signal only at certain instances of time, and for the time in the middle, you keep it constant. Yeah, you keep the amplitude constant. You're going to listen to this, and so as a result, your continuous time signal is converted to a discrete time signal. Yeah. What you do with this filter designs is you again design. So these filters that you see here, so these are all designed for continuous time signals. Yeah, so there are various transforms such as such as the bilinear transformation that you can use to convert an analog an analog transfer function to a digital transfer function. So this can be done fairly easily, and so then the digital transfer function will give you a relation. It will give you a relation between past outputs and current and past inputs that you need to implement to get the current output. Yeah, and that's how the DSP ultimately works. It's an equation that's there on a DSP processor. Yeah, and yeah, so any transfer function any transfer function that you design in the continuous time can be converted to a transfer function in the digital time, in the discrete time mode, And then that transfer function can then be converted to a discrete impulse response. Yeah, and that can easily be implemented using an equation that where you have the current output in terms of the past outputs as well as the past inputs, something like this. Yeah, like here you have y of n is equal to 0.1, y of n minus 1 plus u of n. Yeah. Now, what you would do when you consider an FIR filter is that you would take a IIR impulse response, and then you would truncate that particular IIR impulse response. You will truncate that IIR impulse response and then try to find an equation that kind of gives you the same effect as that. Yeah, then you kind of approximate the IIR impulse response by an FIR impulse response, and that's typically how the whole design process would go. Yeah, you don't really want IIR. You may not always want to implement IIR filters. So when you want to implement them as FIR filters, you would look at truncating the impulse response. Yeah, but that also changes your frequency response. It kind of does bring in high frequency components in your filter. So the moment so the thing really is that there is always a trade-off that happens between your time and frequency. Yeah. So if I'm saying that a signal is infinite in time, yeah, if a signal is very wide in time, it will be very narrow in frequency. And if a signal is very wide in frequency, it will be very narrow in time. As we had just discussed earlier, as you keep making this square wave thinner and thinner, it will become, as you go towards an impulse, this frequency response would just be a flat frequency response. Yeah, the frequency would just be flat. Yeah, that means that your frequency kind of goes to infinity on either side. Yeah, but the moment your time goes to infinity, suppose I have a flat signal on the time graph. Suppose I have a signal that says I have a constant signal, say 2 volts at every instant of time. Then what you will have in the frequency responses, you will have all the energy being contained just at the 0 frequency point. Yeah. So the moment you want to convert so when you have an IIR response, an IIR response would mean that your frequency. So when you have an IIR filter, the frequency response would be kind of closer in time. So your high frequency components will not be very high. Yeah. The moment you convert that to an FIR filter, you will start having oscillations on your frequency response. That means you will have certain high frequency components that your system will begin to allow. So that is a trade-off that you'll always need to do. The moment you convert it to an FIR filter, you might always have certain noise components that your system might begin to allow. Yeah, which is something that you need to be careful to. Yeah, and typically, how will you look at that? You will see that okay, it is going to allow high frequency components. However, I have a speaker, which is the mechanical device. Now, this mechanical device cannot vibrate at those high frequencies because the resonant frequency of that mechanical device is much lower than the frequencies that my FIR filter is going to allow. So typically, if my FIR filter is going to allow those high frequencies, anyway, my mechanical device will attenuate them. So then it doesn't matter to me. So you've got to see that your FIR filter kind of accounts into those things.